Welcome to the AP Physics Workbook tutorial. This is Unit 10, Mechanical Waves and Sound. The section is 10.B, Relationship between the wave speed, frequency, and wavelength. Here's the scenario. You are given a long length of string and an oscillator that can shake on one end of the string at any desired frequency. The oscillator has a display that indicates the frequency. You are asked to design an experiment to determine the velocity of the standing wave on the string. Part A just asks you to write the setup and the procedure. So here I have the image for you. This is a classical example of how the experiment is done. Here's the setup. Attach one end of the string to the oscillator and another end to the hanging mass using a pulley that is attached to the end of a table like seen. Here's the procedure. Measure the distance L, that's from the oscillator to the start of the pulley. Then you're going to increase the frequency on the oscillator until a standing wave pattern seen to form on the string. This is the first one, which is called the first harmonic. You can record as F1. This is centered at one antinode. It should look like something like this, okay, when n equals to 1. Second, you want to increase the frequency of the generator until the standing wave pattern has one node. That's when n equals to 2. It has one node here, which is going to be the second harmonic. Record that as F2. You're going to repeat the process for the fourth harmonic until the fourth harmonic. So repeat it for n equals to 3. That's the third harmonic. That's when it has 2 antinodes. And the fourth harmonic, which is 4 antinodes. All right. Now you want us to describe how you would analyze your data to determine the velocity and the wave of this string. Just letting you know, this needs to be memorized. Okay, this doesn't change. All right, this is the fundamental wavelength and harmonic relationship. The velocity is defined as velocity equals to lambda times frequency. Lambda is the wavelength. The wavelength can be determined by using the different harmonic frequency because you need lambda. See the chart for the details. So here you can see that lambda just equals to 2L. Okay, wavelength 2 is equal to L. Lambda 3 is equal to 2/3 of L, and lambda equals to 1/2 of L. Because remember, this entire thing here is going to be L. What do I mean if you do not see it? So let me show you. This is considered to be, if your teacher never explained it to you here, I can explain to you now. This is considered 1L, correct? The one wavelength would be this. Do you see that? This is why this is considered to be multiplied by 2. Here, this is one complete wavelength. That's why it's considered just L. Here, you have one wavelength. This is your 1, plus you have a half here. 1 and 1/2 gets you 2/3. Right? Yes. Oh, no. Sorry. Yeah, 2/3. 1, 2 over 3. Yeah, 2/3. And this is going to be 1/2 because, take a look. This is 1 and this is 2. So do you see how there's 2 here? So it's, if you want to see the calculation, it's basically 2 over 4. That gets you the 1/2. This is your 1, 2. So this is 2 divided by 3. This is 2 over 2, which is equal to 1. That's why it's just L. Okay? That's it. Okay? That's how you get it. And this is, I think, 2 over 1. Yeah. That's how you get 2L, right? That's if you want to know how to get that. Okay? All right. So let me see this. Okay. The area is going to be determined by the length times width. Okay. This explanation that I'm giving you is the way I show it because it's very easy to look at. A solution that you could also do is actually the slope. The area is the easiest one. Okay, so the area is defined as the length times width. What do I mean by that? Is that if you take a look here, do you see how velocity is just equal to lambda times frequency? This behaves exactly like the area formula. Boom. Okay, all you do is you graph the length of you graph the wave's length on one axis and the frequency on the other. The area would be the velocity, where the wavelength and frequency are the length and width. There you go. Okay, there's ways for you to get using slope here, but the area is the easiest way of doing it. Right. Next, the next part asks you, the student here performs the oscillation and collects the following data. Right. So do you see how these are 2, 1, 0.7? 0.7 is an illusion of 2/3. Okay. So this is in like decimal form is like 0.66666 repeating until 7. Okay. Watch when we do the calculation. Right. So the first one, when it looks like that, the first harmonic. Okay. This is called the first harmonic. It looks like this. Right. Well, I try to draw it the best I can. It's like that. Second harmonic, it has one complete wavelength. Okay. This is the 2/3 one. So 1 right there, 2/3. Okay, and this is 1. This is going to be a half, so this should be 4. So 1, 2, 3. Oh, sorry. 1, 2, 3, 4. Okay. Boom, boom, boom. And this is going to be 0.25, which is I think 1/4. So it's gonna have 1, 2, 3, 4, 5, 6, 7, 8, 8. Okay, 8 wavelengths. So 1, 2. Wait, 1, 2, 3, 4, 5, 6, 7, 8. I try to get it as close as possible. All right. So if you want to know the velocity, all you do is you do lambda times frequency. So V is equal to 2 times 100 equals to 200. And this is meter over second. All right, velocity equals to 1 times 200 gets you 200 meters per second. Again, this is a weird fraction, right? It's like the 0.7. So if you do your 2/3 times 300, right? So if you do the fraction, you would get the better answer. So you do 2/3 times 200. Oh, sorry, times 300. You would get 200 meters per second. Velocity equals to 0.5, so you could do a half times 400. I'm just turning into a fraction to make it exact. Meters per second. 1/4 times 800. Okay, equals to 200 meters per second. You see, easy, right? Easy. Length times width. Okay, here you want to, the way we did it is write an equation for the line of best fit using it to determine the speed of the length. Sketch necessary to solve for the speed of the length. Sketch a line of best fit for your data. So the line of best fit, when they talk about this, they want the slope. All right. So all right. So the way I did it was perfectly fine, but I guess they want it differently. So how I would have done it, it would have been like this, right? I would have done frequency here in hertz, and then I have my boom, boom, boom. Then I have my let's see, lambda. Lambda, 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 lambda. Give me a second here. And the x-axis would be the wavelength, and that's m. Here's the difference, right? Do you see how the biggest you have is like 2? So if you break this up apart, like this can be 2, this can be 1. So then you will need 2/3, which is like probably right here. Then you have 1/2, and then you have 1/4 is right here. Okay, and then let's do this. So this is 100, 200, 300, 400, 500, 600, 700, and 800. All right. So the points would be 1/4, 800. Then you have, right? So do you see how this would be, right? The area right here. Then the next one is 0.5. 0.5 at 400. So it would be here. Okay. And the next one would be 300 at 2.5. Then you have 100, 1 at 200. And then you have 2 at 100. All right. So yes, I know, right? Do you see how this, right, is it curves? But again, you can still find the area. Look, you can still find the area. Do you see? That's how I would do it. You could still find the area, right? Do you see? You would still find the area, right? But for it to linearize, you have to take the square root of something, because right now, do you see it's like this? So you will probably just have to take frequency and 1/2 it. So if you do 1/2 that, if you do 1 over the wavelength, okay, it turns this to basically, let's see, it basically turns this to like 4, 2, 3, and 1. Okay, and then you would have the same frequencies here. So this can be 800, 600, 400, 200, right? And this would still be frequency. Okay, I'm showing you the linearization right now. Then you would probably just graph it like that. 1 at 200, a half is here. So yeah, just a straight line. Boom, 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 boom. Linearize, boom. So this is how it original is. This is what happens when you linearize it. Right? So writing equation, it's basically your frequency. This is your y, right? Think about this is your y. This is your x. Okay? So your y equals to mx plus b. Okay? So this is 0. Right? Because the starting axis is 0. Your x, which is your wavelength, so do that 1 over lambda. Your m is your slope, which is your velocity. Okay? And y would be your frequency. So what is the symbol for frequency? Let me see. F, right? Yeah. Cool. So looks like that. Frequency equals to velocity times 1/2. And this looks like an H, but so it's that. You don't need the plus 0, so it's exactly like that. So velocity times 1/2 lambda, 1 over lambda. Okay. Next, you want to draw a representation of the snapshot taken here. All right. So you just want to count its frequency. I know frequency is just how many cycles a wave is in a given time. So what you're gonna do is count the box here. So I count these as time, right? So this is 1 second, 2 second, 3 second, 4, 5 second, 6, 7, 8, 9, 10 seconds. Okay? So these are seconds. So I count that. In 10 seconds, how many waves are there? Okay? So this looks like it has the most. So B goes first. Because do you see? It has 1. Wait. 1. Oops, sorry. So this would be 1. 1. 2. Right? Then A, it has like 1. Yeah, it has 1. So A is next. Now C and D, who has the most? It looks like I think D has a little bit more, because you see how D has a little bit more of the wave, right? So it would be D, and then C's last. Okay, so just count how many waves they are. That's it, and that is all your solutions for 10B. Again, okay, the way I graphed it was not wrong. Okay, it's just not linearized. Okay, but here when they ask you for the line of best fit, they want it linearized so you can write an equation. That's why I did 1 over wavelength, because remember, this is exponential. Okay, right? Or yeah, exponential. So you have to linearize it by doing 1 over that. Okay, all right, that's it.